We're in Physical Chemistry, Chapter 17, Section 19 now. Now we're talking about nuclear decay. This is first order kinetics. Now the nucleus of an atom is unstable. Now we're going to have minus the derivative of n with respect to time is proportional to n, where n is the number of nuclei. So we get minus the derivative of n. The derivative of the number of nuclei with respect to time is going to be equal to lambda times n. So we're going to say lambda is this decay constant or a proportionality constant. Lambda is not wavelength. So we're going to integrate both sides. We're going to get the integral from the initial number to n of minus dn over n is equal to lambda times the integral from 0 to t dt. So we get the natural log of the number of nuclei divided by the initial number of nuclei is equal to minus the proportionality constant times time. Solve for n, and we get n is equal to the initial number of nuclei times e to the minus lambda t, where e, of course, is the natural number. So that's for radioactive materials, of course. So lambda, solve for lambda, and we get 0.693 approximately. It's irrational, of course, divided by t 1/2, where t is a half-life. Now, if we multiply both sides of the equation by lambda, we get lambda n is equal to lambda n naught times e to the minus lambda t. So we're going to say A is equal to lambda n, and that's going to be equal to activity. A naught is going to be equal to lambda times the initial number of nuclei. So the initial activity is equal to the proportionality constant times the initial number of nuclei. So we get A, the activity, is equal to the initial activity times e to the minus decay constant times time. And this is going to, the activity reported is going to be in disintegrations per second, or DPS. So here's how we have a symbol for an element. We have X, that's the symbol for the element. We're going to have Z, this is the atomic number, which is the number of protons. We're going to have N, which is the number of neutrons. And then we're going to have A, that's the mass number. A is equal to Z plus N, the number of neutrons plus the number of protons. Now, why are isotopes radioactive? Well, it depends on the proton-neutron ratio. For example, there's at least 3 isotopes of carbon. There's carbon-12, 6 protons and 6 neutrons. Carbon-13, which is 6 protons, 7 neutrons. And carbon-14, which is 6 protons, 8 neutrons. So they have the same number of protons, because remember, it's the number of protons that define the element, but they have a different number of neutrons. Now let's talk about beta decay. Beta particle is defined E minus 1, so it's basically negative 1 proton, so it's got a minus 1 charge, and then 0. So the beta particle is an electron, but it comes out of the nucleus, not from an orbital. Now beta plus particle is a positron. This is a plus 1, but it's not a proton, it's a positron. It's an electron with a positive charge. So it's the same as an electron except for charge. Now beta and beta plus are antiparticles. So now we have carbon-14 atom disintegrating into a nitrogen-14 atom. It gives off an electron and an electron neutrino. This bar means anti. It's anti-neutrino, electron anti-neutrino. So the net ionic equation in the context of nuclear chemistry then is going to be a neutron, 0 protons, 1 charge, going to a proton, an electron, and an electron neutrino. That's the net ionic equation for the same carbon-14 disintegrating. So nitrogen-12 does not have enough neutrons to be stable. So we have nitrogen-12 going to carbon-12 plus a positron and an electron neutrino. Now let's talk about alpha decay. So we have a helium nucleus, 2 protons, 2 neutrons, for a total of 4. It's an alpha particle. But this is the nucleus only, no electrons. Remember, a helium atom, since it has 2 protons, a neutral atom would have 2 electrons in orbit also. So this alpha particle, this is the heaviest radioactive particle that they give off. So you have 2 protons and 2 neutrons in one little package. Only the heaviest elements, they'll give off alpha particles. For example, let's say we have uranium-238. Uranium has 92 protons. So it's going to give off one of these helium alpha particles, and then it's going to become thorium-234. Thorium has 90 protons. A thorium atom has 90 protons, but no other particle, just these 2. So the half-life for this is 4.5 times 10 to the 9 years. So that's 4.5 billion years, and that's for uranium-238. But that so on keeps going and going and going until eventually end up with lead-206. And that is the end of chapter 17.